Good evening and good afternoon, I think. Yeah, Professor Chen and Professor Zhao. Hello, everyone. It was my honor to present our work here. I'm Zheng Peng from SKLGP, Chengdu University of Technology. Today, my topic is probabilistic hazard assessments of landslide-induced river damming. This work is a collaboration with master students Wang Sun and Professor Li Tianbing and Professor Fan Xuanmei. So China is one of the countries with most landslide dam disasters. For instance, two successive landslides occurred in Baige village on October 2018, respectively. They damming the Jinsha River on 2 occasions and affected many people and caused a large property loss. So landslide-induced river damming risk assessments and management is one of the main means of disaster prevention and mitigation. So the risk of landslide-induced river damming refers to the expected loss caused by the occurrence of potential landslide in the future. It includes 4 probabilities and 1 consequence. So they are the probability of the occurrence of the landslide, the probability of the elements being at the risk of being submerged, and the probability of the elements being at the points, and the vulnerability of the elements at risk. Today, I'm going to talk about the second probability. It is the probability of raised barrier lake water level exceeding a certain threshold value at a certain point. It is referred to exceedance probability. And we think this probability could be an indicator of hazard of landslide-induced river damming. So the landslide-induced river damming hazard assessments include at least 3 main problems. First, how to quantify the involved uncertainty. Second, how to determine the model input parameters. And third, how to improve the computational efficiency. So to do that, we have introduced the reliability analysis method, the Bayesian back analysis method, and the multi-response Kriging model. So our theory as the past is the key to the future. And our method is from the probabilistic back analysis of past landslides to the probabilistic prediction of future landslide-induced river damming. So here are several main methods. First, we have to construct a runout model to simulate the landslide runout behavior. Here we use the mass flow model based on the basal resistance model. It includes 2 key parameters. They are the friction coefficients and the turbulence coefficients. And both of them here are considered as random variables. And second, we construct a sequential probabilistic back analysis method to calibrate the input parameters based on the observed deposition depth of the slides. Here, because for the Baige landslide, we have 2 slides, so we can calibrate them twice, the first updating and the second updating. And then if, let me shift it, okay. If a potential landslide is similar to a past landslide, the results of the probabilistic back analysis of the past landslide can be used as a radar input for the probabilistic prediction of landslide-induced river damming of the future landslide. So that's, to do that, we have to construct the performance function, and with the aid of Markov chain Monte Carlo simulation method, we can evaluate the exceedance probability of the raised water level height. The fourth is to use the multi-response Kriging surrogate mode. It is because that our method is quite computational expensive. So to To accelerate the computation, we use the surrogate model instead of the raw simulation model. Then we can obtain our results very quickly. This is our implementation process. First, we collect the input random variables and obtain the pre and post sliding games of the next slide. And using the observed deposition depth of the first slide, we conduct the Bayesian backanalysis to obtain the posterior distribution of the random variables. And using this posterior information, we can predict the probability of the river being dammed by the signal next slide. And also, we can further calibrate or update the random variable based on the observed deposition depth of the signal slides, and to again obtain a posterior distribution of the random variable and to predict the future landslide induced river damming events. Here we check the Baige landslide as a study case. It is located on the western back of Jinsha River. Here we can see, and between Sichuan province and Tibet. This is the landslide here. And here we observed two successive landslides occurred in Baige village in 2018. Here we can see the figures from the satellite images. This is before the first slide, after the first slide, and the submerged Bolo village upstream. And this is before the second slide, after the second slide, and the submerged Bolo village upstream. For the first slide, we observed dam heights of about 36 meters. And for the second landslide, we observed dam height about 61.4 meters. But theoretically, the dam height should be 71.4 meters if there was no artificial dam bridge. And then we constructed two numerical models for the first and the second slides and their performance functions. And then we collect the prior information of the friction coefficients and the turbulence coefficients. It is from a worldwide rock slide database containing 168 datasets. They're from America, Dodra, Argentina, Canada, China, and many other countries. And then we can obtain their means, standard deviations, coefficients of variation, type of distribution, and correlation coefficients. In particular, we can see that here we marked in red their coefficients of variation are quite large, 0.69 and 1.15 respectively, which means that there is a large uncertainty in the input parameters. So to conduct the back analysis, we have to collect some observation information from the first slide. This is a post-failure map of the first slide, and we use the 7 observation points. Here we can see in blue points, and we can obtain their deposition depth. So they are located on the border of the deposition area to control both the deposition depth and the affected area. Then we can conduct the Bayesian backanalysis to update the input parameter. And we can see that here, the black line shows the prior information and the red line shows the posterior information. It is obviously to see that their mean value are shifted and their standard deviations are reduced. Then we are going to predict the signal slide. But before that, we have to construct the surrogate model to accelerate our computation. We select the potential area might be affected by the signal slides here marked in red, and construct thousands of surrogate models in this area I mean, there are thousands of great seals. And here we can see their colors. A green color indicates a good approximation, I mean, a good performance of the surrogate model. And as we can see, most of area are in green, which means that the approximation accuracy of the surrogate model is acceptable. Then we can obtain our exceedance probability. This figure shows the PDF, I mean the probability density function of the raised barrier lake water level. And we can also obtain their 99.7, I mean 3 sigma confidence interval. And it's found to be 51 meters to 74 meters. And also we can generate the exceedance probability curve of the raised barrier lake water level, and we can find their exceedance probability for any threshold value. For instance, here we found this probability of exceeding 60, 65, and 70 meters were about 92%, 73%, and 35% respectively. And moreover, we can project this probability interval onto the satellite image. Here, we can see the first figure shows the most probable barrier lake depth with an exceedance probability of 50%. And the second figure shows the observed barrier lake depth. Yeah, they are agreeing with each other quite well. And here, this figure shows the enlarge of the Bolo village upstream. This is the Bolo village, and this is the Landslide. And here we can see several lines in different colors, in which the black one shows the upper bound of the water level. The purple one shows the lower bound of the water level, and the red one shows the one with 50% exceedance probability, which means the most probable one. And here, the blue one and the yellow one is the observed and theoretical submerged area. It is surprised to see that both of them, I mean the observed and the theoretical submerged area, were within our predicted interval. It means that our proposed model has a good prediction performance, and it can be applied to the future landslide induced river damming prediction. Okay, now we can predict the future events. But before that, we can conduct another back analysis based on the observation information from the signal slides. Here we select 10 observation points and their deposition depth. Then we conduct the back analysis, and we can see that the friction coefficients and the turbulence coefficients were both, I mean, their standard deviation were both reduced again. This will improve our confidence in our prediction. Then we are going to predict the future unstable rock mass. On October 2020, we investigated the bike landslide again, and we found 2 unstable rock mass. They are the B1 parts and the B2 parts. Their volume are about 2 million and 7 million cubic meters. And we consider 3 scenarios, I mean, failure of each parts and their combination. And before the prediction, we also have to construct the surrogate model for the 3 scenarios. And here we can see the green color indicates a good surrogate model. For the second and the third scenario, the surrogate model is good, but for the first one, it is not so good because we can see many red color here. Red color indicates a bad approximation. But however, here we can see that the potential area might be the area where the landslide deposition located might be here, this part. So in this part, they are most in the green color, means a good prediction. So that's in general. I mean, in general, we can say that the approximation accuracy of our surrogate model is acceptable, but not so good. Then we can compute the PDF of the three scenarios and to find their 3 sigma confidence interval. For the first scenario, its interval is about 20 to 40 meters. For the second scenario, the confidence interval is about 54 to 60 meters. And for the third one, it is about 60 to 70 meters. And also here in this figure, I mean the exceedance probability curve, we can find this probability exceeding any threshold value. And also we project the interval, the confidence interval onto the satellite image. The figure on the left shows the.
Interrupt you. 2 minutes left.
Sorry. Okay. All right, yeah. Okay, here we can see on the. Okay. I got it. Okay. On left, we can see the barometric depth with a probability of 50%, and this is potentially submerged Bolo village, and here is enlarged of the Bolo village government here. And we can see the black line shows the upper bound, blue line shows the lower bound, and the red line shows the most probable events. And here we can see that the Bolo village government will be probably submerged. And for the second scenario, here we just focus on this figure. We can see that the Bolo village government building will be certainly submerged. And for the third one, also very similar to the second, the Bolo village government building will be totally submerged. And also we can obtain many other information. For example, the 3 sigma confidence interval of the barometric length, the water storage volume, and the number of submerged houses in Bolo village. And these results can be directly used for decision making of disaster prevention and mitigation. Okay, we just shift to the potential problems and the deficiencies of our method. First, we think it is very important to identify the landslide. I mean, to find where is the landslide, and also to determine the volume of the landslide, because an incorrect volume prediction will result in an incorrect prediction of landslide dam. And also, we have to conduct other risks, for example, the dam break risk assessments. All right, that's all about our work. Thank you for your attention.